Hello everyone, my name is Barrick, and today I will be demonstrating my machine learning project, AIRIS. AIRIS is a causality-based approach to machine learning. Rather than using neural networks to analyze large sets of data for statistical probabilities, AIRIS uses what I call reinforcement inferred causality. It observes and infers cause and effect relationships to build an internal model of the world. It uses that model to make predictions and plan sequences of actions to achieve its goals. And it refines that model any time a prediction doesn't match reality. That results in some very useful features. It works with small data, it's explainable, it's transparent, it's goal agnostic, and it continuously learns. But more on those later. First, what is it and how does it work? This is a simple grid world puzzle game. The AI controls the robot and can move in the 4 cardinal directions. The inputs to the AI are a 2-dimensional array of values that represent the screen, and a 1-dimensional array that represents the score. Collecting a battery gives +1 point. The goal we give the AI is to increase its score. A quick disclaimer, the imagery in this section of the video is handcrafted and not actual output from an AI. Actual AI footage is later in the video. The first step in reinforcement inferred causality is to create an internal model by copying the current inputs. The AI then uses that model to attempt to make predictions about what future states will look like after it performs an action. But it fails because it doesn't know what its actions do. So it randomly chooses an action to perform and observes the results. Let's say it chose the action move left. What it observes is that 2 values changed. The 0 to the left of the 1 changed into a 1, and the 1 to the right of the 0 changed to a 0. From this observation, it creates 2 causal rules. Rule 1. If the action is move left, and the value in the position we are evaluating is a robot, and the value in the position to the left is an empty space, and the score is 0, then the robot will change to an empty space. Rule 2. If the action is move left, and the value in the position we are evaluating is an empty space, and the value in the position to the right is a robot, and the score is 0, then the empty space will turn into a robot. When both of these changes are combined, we get the robot moving left. Notice that it included the score even though the score did not change. That's because the score is a separate type of input than the screen, and they may or may not have a causal relationship with each other. So it's assumed that they do until proven otherwise. Now that it has some rules, it can apply these rules to its internal model to start making predictions. Again, it creates the internal model by copying the current inputs. Then it makes predictions about future states after it performs an action. It copies the current model state into a new model state, then applies the rules to the new state. The first 3 states it predicts are the same as before because it still doesn't know what those actions do. But now it has rules that can predict what will happen when action 4, or move left, is performed. Despite their appearance, these rules are not traditional if-then statements. Most of the conditions have a confidence that is calculated between 0 and 1, rather than a binary true or false. The confidence of each condition is then summed and divided by the total number of conditions to get the confidence of the rule. Whichever rule is calculated to have the highest confidence is the one that is applied to that particular value in that particular location. Let's say we're going to move left. First, we calculate Rule 1's confidence. We'll look at this screen location, which is the robot value of 1. Then this screen location, which is the empty space value of 0. And the score is still 0. So the confidence is 100%. Now we check Rule 2 against the same screen locations. This is a robot, not an empty space, and this is an empty space, not a robot. The confidence is 50%. The rule with the highest confidence is the rule we apply to the value in that position. The same process occurs for the empty space, or 0, that is next to the robot. The confidence of a prediction is the sum of the confidence of the applied rules divided by the number of applied rules. In this case, we applied 2 rules, and each rule has a confidence of 1. 1 plus 1 equals 2. 2 divided by 2 equals 1. So the confidence of this prediction is 1. So far we have 2 states, the current state that we'll call C, and the first predicted state that we'll call S1. Next, it generates a new set of predicted action states from S1. The first 3 actions are still unknown, But move left produces another prediction with a confidence of 1 that we'll call S2. It generates more predictions, but it runs into a problem with S4. The first position it evaluates is the robot, but the value to the left is a wall, not an empty space. So the confidence in this rule is 3 out of 4, or 75%. The first rule still has the highest confidence, but it's not 100%. Regardless, it applies the best rule to the value. Now, it checks the position where an empty space normally is, but finds a wall. The second rule has the highest confidence, so that is what is applied to this position. The total confidence of the prediction is only 0.75 plus 0.75 divided by 2, or 75%. Now, obviously, to us, this prediction is wrong. The robot isn't going to smash its way through the wall. But the AI doesn't know that. It's only performed one action ever, and that action resulted in the robot moving left. It doesn't know that anything can stop it. With a low prediction confidence of only 75%, it stops generating new predictions from that state because it is uncertain that its prediction is accurate, and future predictions from that state may also be inaccurate. Now that it's done making predictions, it's generated an action state graph using its internal world model that it can use to make plans. If you know what a Markov decision process is, this is pretty similar. First, it searches for a state where score increases, as that is the goal that we have given it. Unfortunately, that state doesn't exist. So, it starts over and searches for a state with a low prediction confidence. This is called the intrinsic subgoal, and the AI will always fall back on it if it can't figure out how to achieve its primary goal. Because you never know. It's possible that smashing through the wall will increase its score. Tracing through the graph from the current state to the subgoal state, we get the sequence of actions that the AI will need to perform and the predicted outcomes of those actions. The AI then performs the sequence of actions, and at each step it is checking the real inputs against its predicted inputs to make sure that they match. And when it reaches the wall, it sees they don't. Its prediction failed, and it has to create new rules. Now it has 4 rules to work with, and the next time it tries to predict what will happen when it moves left against a wall, it'll be 100% confident that it won't smash right through it. Let's say that the AI has learned the rules that it can move in other directions and that walls stop it. It does not yet know how to achieve its goal of increasing its score, but its prediction for moving against a battery results in a low prediction confidence. That flags that as an action that satisfies the intrinsic subgoal. So, it tries it to see if its prediction is correct or not. Now, it's created an important new set of rules. It now knows how to satisfy its primary goal of increasing its score. But there's an interesting side effect. The prediction confidence for all of its actions just dropped. Why? Because so far, all of the actions it has taken have been when its score was 0. It has no idea how a change in score will affect things. Maybe it can smash through walls now. Who knows? It won't generate new states from low confidence predictions, which is everything now, so it watches while it moves left to see if its prediction is still accurate. The result is exactly as predicted. Something is wrong with the rule. It turns out that the value of the score has no effect on it moving left. So it reevaluates the rule, finds any values that are different, and discards them. Effectively, it uses a classic process of elimination to refine its rules and improve its predictions. Let's give it a small challenge. We'll put the battery down this hallway. Now, the AI will have to plan a route to get to the battery. The process of generating the internal model results in a large action state graph that is perfect for pathfinding. It'll just keep generating a larger and larger graph until it finds either a state with low prediction confidence or a state that results in increasing its score. Then, it traces the graph to get the sequence of actions, performs the actions while monitoring for prediction failures, and achieves its goal. From these basic principles, it can learn and perform increasingly complex tasks. Let's add a new obstacle, a locked door that can be opened if the robot collects a key. Let's also add a new value to its one-dimensional input array that we'll call key, and it will represent whether we have or have not collected a key. The goal we give it doesn't change, just increase score. There are now a couple of low confidence states in its internal model graph. It has not moved against a door, nor has it moved against a key. So, both of these have low confidence. It could go for either one, but let's say it chooses the door. It moves against it and learns that it's just like a wall. Even with this new knowledge, it still cannot create an action state graph that results in it getting the battery. So now it moves against the key, as that is the next lowest confidence. The key value changes. And just like when it first got a battery, all of its predictions now have lower confidences. So, to satisfy its intrinsic subgoal and refine its rules, it will move around, push on walls, then push on the door, and learn it can now open. And now it can create a graph that achieves its goal. Reconfiguring the room or adding more items does not affect its problem-solving capability, because it is based on causal reasoning. It simply applies the same fundamental causal rules to the new configuration and can generate an action state graph that results in achieving its goal. This is a larger version of the Grid World puzzle game that I created as a testing ground for the project. The inputs to the AI are a 2D array of screen values, which is represented on the right with colored blocks instead of numbers, as that's much easier on the eyes, and a 1D array of score, number of keys collected, and number of fire extinguishers collected. The only goal we give it is to increase its score. There are 13 levels and a variety of obstacles. One-way arrows, where the robot cannot move into the space from the direction the arrow is pointing, but is free to move into it from the other 3 directions. Doors and keys. Fire, that resets the level on touch and subtracts 1 point from the score. And a fire extinguisher, that can put out 1 fire. A level can have any combination of these obstacles, and some of the levels have extra items that are not necessary to collect to complete the level. Some levels have pitfalls, where if the AI does not use the items wisely, it will not be able to complete the level at all. From here on out, this is a real IRIS in action. An unoptimized minimum viable proof of concept written in Python, but real nonetheless. I've only edited the footage to slow it down and remove pauses where it plans what to do next. This is all one continuous episode. Beating a level moves on to the next level. Dying in a fire restarts the level. Beating the game restarts it back at level 1. Only after beating the entire game 3 times does the episode end. As you can see, this one's hard. Lots of things to grab and use, and very easy to get stuck and have to restart the level. This was the Nemesis level for earlier versions of IRIS. Almost all of them couldn't beat it, and those that couldn't do it consistently. Remember that the only reward it's receiving from the environment is when it collects a battery, which satisfies the goal that we gave it of increasing its score. For some levels, like this one, that reward is very sparse. All of the multi-objective planning, collect the key to open the door, to collect the extinguisher, and another key to open another door and put out a fire, is purely the result of it modeling what it needs to do to get through the obstacles and achieve its goal. Now that it beat the last level, the game loops back to the start, and you can immediately see how much better it is with the knowledge that it gained the first time through. It still has a little trouble with the nemesis level, but not nearly as much. By the third time through, it's found highly efficient ways through most of the levels, avoiding extra items, pitfalls. Even the nemesis level doesn't pose a challenge anymore. And that's the end of its first episode. But those were just the same levels over and over. What about a level it's never seen before? Let's start a new episode with this new level loaded in and set to repeat. I'd say the answer is yes. Now that we've seen what it can do, let's go back and talk about the features that I mentioned at the beginning of the video. Small data. Unlike traditional reinforcement learning that requires hundreds, thousands, or even millions of episodes to train, AIRIS takes just 32 time steps to go from blank slate to first achieving its goal, 4,612 time steps to beat the game the first time, and only 921 time steps to beat it the second time, and all in one episode. Explainable. All of the rules that it generates through actions and observations can be translated into human-readable formats, along with any additional metadata that we choose to include, such as when a rule was created, what the inputs were at the time, how and why the rule was refined, or any other info that we might find useful. Transparent. Before executing any action, the AI must plan out what it's going to do in its internal model by creating an action state graph. This gives us the opportunity to look directly into the planning, reasoning, and motivations of the AI before, during, or after the AI has taken action. We can see the confidence that it gives each action state, why it assigned that confidence level, what rules it applied, what its predictions are, why it chose the end state of its plan as its goal, how far ahead it planned, and anything else we may want to know about what it's doing and why. As a basic example, I created this Mind's Eye tool. After making a plan, but before executing the plan, the AI outputs its current action state graph to this tool. I can then use this tool to see what its plan is. I can also browse through the rest of the action state graph to see what other states it thought of. The AI will patiently wait until I send a command to continue. Then, it'll show me what its next plan is, and so on. Goal agnostic. The process of inferring causal relationships is independent from the primary goal of the AI. That allows us to change the primary goal of the AI at any time. Giving the AI a different goal just changes what state the AI searches for in its internal model graph. In this example, this trained AI has the usual goal of increasing score. Right before it completes the level, I pause it, change its goal to decrease score, and let it continue. It immediately abandons collecting the battery and goes straight to the fire. And it'll continue to throw itself into the fire since that is its new goal. I pause it again, switch its goal back to increasing score, and it resumes its quest for the batteries. Here's another example. I put a trained AI back at level 1, but gave it the goal of decreasing score. Now this poses an interesting problem for the AI. Batteries are now bad, as they do the opposite of its goal. And since it won't encounter fire for several levels, it has no way to achieve its goal. So, it falls back on its intrinsic sub-goal of exploring states with the lowest prediction confidence. There aren't many for it to choose from, as most of its rules have been pretty well refined. But it finds a few, like moving through arrows in ways that it hasn't needed to before. It may look like its goal is still to collect the batteries, but every time it collects one, it's failing its goal. There just isn't anything else for it to do except fail its goal. So it fails its way through the levels. Here, I skipped all the easy fire levels and jumped it straight to the end, which has the hardest fire to reach, and it goes right for it. Continuous learning. As we've seen, with every action it takes, IRIS is analyzing its inputs to see if it needs to create or refine its rules. It does not need a curated set of training data. It can adapt quickly to unfamiliar situations, and it does not suffer from catastrophic forgetting. These are some great features, but let's talk about its current limitations. You may have noticed that I've only shown it working in a puzzle game that I created. Here's why. It can't yet discern cause and effect relationships that are independent of its own actions, like other characters or objects. It associates its own actions as the cause of those other events and quickly gets hopelessly confused. It also doesn't have temporal reference. Take this picture of a ball. We can't know the direction and speed of the ball without referencing where it was in the previous moments. IRIS is only looking at a single picture of the ball, so it fails to be able to predict the ball's future movement. These critical limitations prevent it from functioning in anything but the most basic toy environments for now. But these are not insurmountable problems, and I am making progress on them, even if it may not really look like it from this particular clip. Once these limitations are overcome, it will be able to operate in much more dynamic environments, like Atari games, or the ProcGen benchmark from OpenAI, or any other environment that I can throw at it that I have the hardware to run. I'm sure that there will be even more limitations to uncover and overcome as both the capabilities of IRIS and the complexity of the environment scale up. Right now, I'm running all of this on a 4-year-old gaming laptop, but I expect the hardware requirements will quickly scale up as well. Even so, I can't wait to discover what it will be capable of, and hopefully the next update video will be IRIS playing Atari.